Hi everyone, I'm Suhail. I'm a Marie Curie Fellow at the Institute of Astronomy in Cambridge, and today I'll be talking about some of our recent work on the Zwicky Transient Facility, calibrated to the tip of the red giant branch in a uniform distance ladder. Now, I'll specifically be talking about this as a method for measuring the Hubble constant and moving towards the JWST era in the future. So details of both the projects that I'll be talking about in the first data release and the uniform distance ladder are in these two papers. And this is work done in collaboration with the ZDF Cosmology Working Group, as well as the Carnegie Chicago Hubble program. So I'll start briefly with a motivation for why it is that we want to look at both the Hubble constant as well as why type 1e supernovae are so interesting. Secondly, I'll move on to talking about the work that we did for the first data release of the Zwicky Transient Facility type 1e supernova sample, and then move on to the uniform ZTF tip of the red giant branch distance ladder. What was the idea and what is the pilot study about, as well as finally, what in the proof of concept study we got as H0 and looking forward towards the big sample calibrator for getting precision estimates. So the motivation, we know that the Hubble tension, that is the tension between the inferred value of the Hubble constant from the early universe and the direct measurement from the late universe, is one of arguably the biggest questions in cosmology. Could this be a sign of new cosmological physics, a breakdown of standard lambda CDM, or is it unknown sources of systematics? And for this, what we really need to do is look at unknown unknowns currently. And that's something that can be seen from the plot on the right-hand side, where we see that the Cepheid distance ladder is in extreme tension with the Planck measurements. However, the tip of the red giant branch is not so extreme in its difference from Planck. And the way in which we can sort of look at this is firstly look for unaccounted for sources of systematics. So that's still within the purview of known unknowns. So what kinds of systematics have we not accounted for? And this is something that I have looked at in terms of near infrared observations of type 1e supernovae, as well as like combining the calibrator rung with all the way to high redshift type 1e supernovae from the Pantheon compilation. What today I'll specifically be focusing on is an independent distance ladder, so something that is independent of the Cepheid variables, and an independent way of uniformly calibrating the type 1e supernova luminosity in order to infer H0. Additionally, what is also exciting is doing novel absolute distance measurements for alleviating and understanding this tension, which is through lens transients and standard sirens. Independently, this is something I'm quite excited about, but not something I'll be talking about today specifically. So since the center of my talk is going to be type 1e supernovae, just a brief overview of what these are and why they're exciting for cosmology. So type 1e supernovae are bright stellar candles or like cosmic beacons that can be seen in both the nearby and the distant universe. And they are excellent distance indicators, but they're not standard as the candles come. They need to be calibrated by using relations between the luminosity and light curve shape, luminosity color, as well as the dependence between the Hubble residuals and host galaxy properties like stellar mass, or when possible, like for low redshift samples, specific star formation rate, or even local properties. Now, they exist in all kinds of galaxies, young and old, and they were also instrumental in the discovery of accelerated expansion. So they're extremely powerful as distance indicators, both for nearby and distant universe studies, so both for H0 as well as dark energy. So before talking about the ZTF sample and what are the benefits of ZTF as a survey and a supernova sample, just how exactly is it that H0 is measured from the distance ladder, very sort of quick overview. So here, this is adapted from the SHU's 2016 distance ladder analysis. While I'll specifically today be focusing on the second and the third rung of the distance ladder, it's essentially trying to do as much of a like-for-like comparison going from our neighborhood all the way out into the nearby Hubble flow. So it's calibrating the Cepheid period luminosity relation with multiple independent anchors like the Large Magellanic Cloud, Milky Way parallaxes, as well as a major distance to NGC 4258. And then moving from there to having Cepheid distances in the galaxies that also have type 1e supernovae. Here we're essentially rate limited in the small volume that can be probed with HST right now. And that's where the key to pushing farther with JWST will come about. And then we have about currently in the Hubble flow a couple of hundred type 1a supernovae that have been sort of assembled from several different telescopes and some surveys that have very specific selection effects. And some of that information is lost, and it's basically coming from lots of different sources that can be very heterogeneous. This is also the sample that forms the low redshift anchor for dark energy studies, and is essentially something that we had looked at, but I won't be talking about today, is how to have a homogeneous combination of everything that goes from calibrators all the way out to the high redshift type 1a supernovae. And this is the method that is used in SHOES 22. So basically calibrating the luminosity of these type 1a supernovae using primary distances to these type 1a supernovae, which are typically in a distance that's below 40 megaparsec, but can be pushed out in the future, is the main way in which we measure H0. And this has been done most prolifically with Cepheid variables and the tip of the red giant branch method. So moving from the literature sample to type 1a supernovae from the Zwicky Transient Facility. Now, ZTF is a wide field optical survey that is observing the night sky, or was observing on a 3-day cadence, and is now observing the night sky on a 2-day cadence in the G and R bands. It has a huge field of view of 47 square degrees. And compared to its predecessor, the Palomar Transient Factory and the intermediate Palomar Transient Factory, it surveys the sky more than an order of magnitude quicker. Now, it's just not just the discovery capabilities of the Palomar P48, where the Schmidt the telescope has this huge field of view camera, but also along with that, the SED machine on the Palomar P60 that has been a workhorse instrument to classify the transients that are discovered very rapidly. And the plot on the right-hand side is the all-sky distribution of the first data release of type 1a supernovae from ZTF. So this is around a little less than a year of observations. And already it has discovered around 800 type 1a supernovae in the nearby Hubble flow. In its first phase of operation, which was the 3-day cadence public survey, and along with that, like a third filter in the I band, it has already observed around spectroscopically classified type 1a supernovae, which are around of order a few thousand. Now, this is going to be part of the second data release, something I'll talk about in the outlook. But even with like the DR1 sample, because it's all sky and it is untargeted, that is, it's the same telescope to discover and follow these up, we can actually do more than just W or H0. We can actually do large-scale structure studies, so it's an entirely new probe of growth of structure. It can also be used to do like anisotropy of H0 as well as bulk flow studies. And because of its large, homogeneously observed sample size, it will be an excellent legacy for the low redshift anchor to do dark energy studies with the Rubin Observatory and the Roman Space Telescope in the future. So there's a rich data set with which we can do several different kinds or answer several different kinds of scientific questions. So this is a sort of summary of the characteristics of the Hubble flow sample. So this is looking at those that are in the redshift region between 0.015 and 0.1 and comparing it to the current low redshift sample. So we see that the current low redshift sample has a median redshift of around 0.03. ZTF has a median redshift of around 0.06. So having it as sort of twice as high in the low redshift Hubble flow sample, we are less prone to systematics from peculiar velocity uncertainties. Moreover, because they have been discovered earlier in comparison to the median from the literature, that's a lower panel here, we can actually use the rising part of the light curve to improve standardization. And that's something that has been shown in the literature to improve the intrinsic scatter. So we can start to build upon the existing SALT to model, retrain it, and then start to improve the distances to these type 1a supernovae. And that's something that you can see here for even at the median redshift of around 0.06, we get quite a significant sampling on the rise. So computing something like a sigma RMS as a diagnostic, we see that even with a preliminary sort of pipeline that has been used for the reduction, we get a sigma RMS, which is very comparable to the current low redshift sample that has been worked on quite a lot in terms of its photometric calibration. So it is showing the promise of ZTF as a Hubble flow sample. So in order to get the distance ladder, it's not just the Hubble flow that we need, but we also need the calibrator sample. And essentially, ZTF has already, in its first few years of observations, found a few tens of type 1e supernovae in the distance where we can get accurate independent distances from space, so whether from Hubble or James Webb in the future. And essentially building a distance ladder that has the same untargeted survey to discover the calibrators as well as the Hubble flow sample is extremely important, because of all these different heterogeneous photometric calibrations, there can be sources of systematics that are unknown, that have crept up into the estimate. Now, in order to do this, we need both those samples to be a volume limited sample, in the sense that they should be coming from all possible environments of type 1a supernovae. And the Cepheid distance ladder, while it has been assembled from a large legacy of type 1a supernova distances, not only does it come from different instruments and surveys, which each of them have their individual selections that are coming by, and it's not just one single homogeneous survey, it also is a primary distance indicator that is preferentially only in young star-forming environments. And that's what I'll talk about in the next slide. In the Hubble flow rung, we see that around a few hundred type 1a supernovae that were there in this redshift regime will now soon be replaced with around 3,000 from ZTF DR2, but DR1 already has around 750 Hubble flow type 1a supernovae. So why do we move towards the tip of the red giant branch? And I think this figure illustrates that, the relative benefits. So we see that Cepheids, one, they are preferentially found in young star-forming environments. They're also in quite crowded disky regions of galaxies, whereas the tip of the red giant branch is seen in outer halos. So there's less likely to be any systematics from crowding bias or extinction and metallicity effects, which have been shown to be significantly impacting our inference of the Hubble tension, or both its central value and the uncertainty. And because of them being near infrared bright, we can do tip of the red giant branch out to larger distances in the future. So the reason why, and we can see this again, illustrating the point of tip of the red giant branch being in both old and young host environments of type 1a supernovae, we see that ZTF, compared to the literature, is probing the entire distribution of host environments. And this is something that's important, given that we can need as much of a like-for-like comparison between the calibrator and the Hubble flow sample. And having the tip of the red giant branch distances, which are probing the entire distribution of the host galaxy properties that type 1a supernovae exist in, we are a lot less prone to being biased with the TRGBs, but also what we see that we can then have a volume limited comparison between both the calibrators and the Hubble flow, and then look at subsamples with demographics, whether or not we can find ones that have a smaller intrinsic scatter. So what we did was we started with what data we have. So we have this well-studied, well-measured Hubble flow sample from ZTF. Then we took all of the objects that we have within a 20 megaparsec region. So that's within the feasibility of HST with C3. And of the ones that were feasible, there was just one that had a good distance or had good enough data to compute a good distance. And this was 21 RHU. We can see the exquisite sampling that we have from ZTF for this. So we got the regular program, but then also for the ones that are the nearby ones, we just targeted them with a much better cadence than even the 2-day cadence that was there for ZTF phase 2. So we just got a daily cadence for these ones. And using the standard SOL2 method, we get a supernova distance. Using the HST data, we took all of the data that's there from ACS and WIFC and we basically took the fields that were in the outskirts of the galaxy, so not impacted that much by the dust in the central region of the galaxy, and essentially get a tip of the red giant branch distance using the standard Carnegie-Chicago Hubble program pipeline. So this is what the current ZTF distance ladder looks like. Here we have both this. In this case, the proof of concept is a single object, but the Hubble flow sample is also DR1 volume limited. And so we don't just take everything till 0.1, we just take everything within a volume around 0.06. This is where we're volume complete. And then we can use, because it's a carefully constructed selection function using the bright transient survey, we can use that to then sort of have a proper selection function constructed for the entire sample all the way between 0.015, that's the nearby Hubble flow, till 0.1. Currently, this is just to demonstrate for the DR1 volume limited sample, because we just have a single calibrator, so the Hubble flow will not be dominating the uncertainty. So this uncertainty on H0, which is around 8%, is largely dominated by the fact that we just have a single calibrator. And now in HST cycle 30, we have time to get more calibrator galaxies and increase this sample such that we can start bringing this uncertainty down close to 3% with just HST itself. We also see that the sample selection, like whether we use full volume limited or like full entire out to redshift 0.1, is not something that impacts H0 very strongly. We also fit with SOL2 and Snoopy, and we don't find that that changes H0 very significantly. ZTF DR2 will improve this by about an order of magnitude. So we took only the ones that have spectroscopic redshifts from the host galaxy. ZTF DR2 will have the full range of 3000 Taiwanese supernovae with redshifts. So the outlook here is that now with James Webb, we will be able to probe a volume of around 80 megaparsecs. ZTF has already observed over 100 Taiwanese supernovae with accurate supernova distances. And with the augmented DR2 sample, we will then have a volume limited calibrator sample that has a large number of absolute distances. And we can reach below around a 1.5% level accuracy on H0 with this entire range of distances that we have. So the supernovae already exists, and now we will go ahead beyond the 40 megaparsec level and get distances with James Webb. So conclusions that while systematics from other sources are subdominant, looking at an independent distance ladder, we can start beating down systematics with a uniform calibrator and Hubble flow sample, both of which are volume limited. So thank you for your attention.